Hi, thank you for the introduction. So today I'm going to talk about functional credentials. Can you hear me well? And so this is a joint work with Dominic Goldberg, Matteo Maffei, Max Frapkin, Dominic Schroeder, and Mark Sinkin. Let me give you a brief introduction about classical authentication mechanisms. I hope you're all familiar with it. Normally, like this is better. Sorry. So classical authentication mechanism exploits several features of the carrier, which might be the possession of a token, knowledge of a secret, or some unique physical features. Now, this has obvious problems, which is a very well-known topic in the literature. It's the fact that the verifier, whenever a naive authentication mechanism is used, can just track the user and can just uniquely identify it based on his credential if this mechanism is executed in a naive way. So it has been apparent from so many years of research that we need two properties at least of authentication mechanism, which are the soundness. Soundness means that the prover cannot fool the verifier into accepting some capabilities that doesn't have, and anonymity, which means that beyond the output of the protocol, the verifier should not learn any additional information about the carrier of the credential. So let me give you a very quick introduction on how anonymous credential works. So we establish a common ground of notation. Typically, users request their credential token, which in this case is a key, to an authority, to an issuer, and based on a certain set of credentials. In this case, the guy is male and greater than 18, and he gets the appropriate credential. And later on, he can interact with a certain verifier and convince that he satisfies a certain policy, whether this policy could be male or greater than 18, in such a way that the verifier does not learn anything but the fact that the prover satisfies this policy. And he can do that thanks to the token of the issuer. Now consider the following scenario. Let's take a data owner that outsources a database for a cloud service, and he wants to outsource also the management of the data set, and of course he wants to give selective access to his data to certain clients. So he entrusts the cloud to make access control on his behalf. Okay. So whenever users comes in, of course the credentials are distributed to appropriate users. So whenever users comes in, he can prove to the cloud that he's entitled to write an entry if he satisfies a certain policy. In this case, he needs to be greater than 18. But this has certain privacy concerns. For example, in this example, one thing that the cloud may ask is, even though it doesn't know anything about the carrier of the credential, why does this guy need to be greater than 18? So what's in this data, right? So this itself is an information that gives a non-trivial leakage to the cloud, which we don't want. And ideally, we encrypt data because we don't want to reveal anything about the cloud. And the fact that we put a certain policy associated to a certain data, it gives already some information, right? And to convince you that this scenario is meaningful, I give you a concrete example where this is actually a concern. If you consider oblivious RAM intuitively wants to hide the access pattern to the eyes of the database, in the sense that whether you write on an entry X or on an entry Y should be indistinguishable to the eye of the cloud. In this case, if you want to perform access control over this data, this leakage is unacceptable. So it's in inherent conflict with obliviousness. So we need a different solution for that. So that's why we formalized the notion of functional credentials, which we believe to be the good solution for this problem. And in this work, we formalize the security definition. We propose a generic construction that uses predicate encryption in a black box way. For those of you who are familiar with that, it means that you do not assume any specific instantiation, but you take any scheme and it just works right out of the box. You don't have any expensive step on it. Just only the code that is used for this primitive is run. So if, for example, running a zero knowledge proof over that is not allowed if you want to have a black box instantiation. And we implement this. Unfortunately, we don't have a full-fledged implementation for any possible function, but we have to restrict ourselves to constant depth Boolean formulas, and you'll see why in a second. So let me give you a quick overtour about the notation of functional credentials. The scheme is relatively simple. We define a setup algorithm which is run by the issuer, a grant credentials which is run by the issuer again and takes as input the master secret key, and this is used to grant a certain credential given a set of attributes A. Now the key difference with respect to classic and anonymous credentials is the presence of this delegate algorithm, which does not delegate a credential, but instead delegates a token which is used to check against credentials. So you can see this as a token where the policy is embedded inside this token. You can test it against several credentials, but beyond the output of the protocol, you should not learn any information of the policy which is embedded in this token. And so the first protocol is the classical anonymous authentication, whereas the second protocol has the key difference that uses indeed the delegation token and on the verifier side. So you can think this as a blind verification of credential. So the verifier does not really know what it's checking, but he makes sure that the issuer, sorry, that the carrier satisfies the policy which is encoded in this token. So what are the properties that we want to make sure, that we want to ensure? So the first is unforgeability, which is also I also mentioned it as soundness. Is the fact that a carrier which does not satisfy a certain policy should not be able to fool the verifier. In this case, this Hello Kitty should not be able to prove that she is male and greater than 18. Anonymity says that two provers which are not, for which the protocol returns the same output, should not be able to, you should not be able to distinguish among them efficiently. And finally, the most important properties of this work is policy hiding. Policy hiding says that if I give you a certain token, you should not be able to tell what's the policy embedded in this token beyond what is trivially leaked by the protocols that you run on them. Of course, the verifier that possesses this token, he can test it against credential. This is a functionality requirement, but beyond the output of this protocol, you should not learn anything about the policy that is embedded in this token. Okay, so what's the main tool? What's the main tool to construct a functional credential? So the main tool that we use is predicate encryption, and predicate encryption is a very powerful cryptographic primitive, which is characterized by the following algorithms. So again, there is a setup, and you can see already the similarity here. There is a key generation that takes a set of attributes and returns a key for these attributes. There is an encryption that takes a message and a policy and encrypts this message against this policy. And okay, I'll skip forward to the decryption. So you are able to decrypt a certain ciphertext if the policy associated with the ciphertext matches the attributes associated with the key, which is P of A equal 1. Also, we need to additionally assume that this predicate encryption supports a re-randomization algorithm. This is more of an algebraic property of the scheme, but it is satisfied by most of the instances that we know. So predicate encryption for inner products was introduced by Katzahai and Waters in 2008, and a breakthrough result by Garg et al. Propose a functional credential, a predicate encryption for any function, but it's very slow and from non well understood assumptions, so it's very hard to implement. I think we're not at the point in time where we can implement this scheme yet. Okay, so how does our construction work on a high level? My objective here is to give you a high level intuition of the construction, and if you're interested in more details, I refer you to the papers. Again, there is an issuer. The issuer as a set of public parameters, which in this case are the public key and the secret key of our predicate encryption scheme. And a credential consists, for a set of attributes A, consists of a key under the secret key of the issuer, whereas a token consists of an encryption of a given policy of 1. In this case, it can be any fixed string, but in this case, we take 1 for simplicity. So it's not really important what you encrypt there. What's important is the fact that you embed the policy there. Okay. So let's take a look how we verify. So the challenge here is, so the approach becomes relatively easy once you throw non-interactive zero knowledge to it. But the challenge here is that we don't want to do that because that makes things usually way less efficient. So we want a black box construction in the predicate encryption scheme. How much time do I have left? 4 minutes, perfect. So give you a quick intuition what's going on. So recall that the prover holds a key, whereas a verifier holds a ciphertext. And the main idea of this protocol is that if the prover satisfies the policy, it should be able to decrypt any ciphertext, right? So first thing that the two parties do is to run a coin tossing protocol with a certain random coin, which are denoted by the dices. Then the verifier takes as input this randomness, re-randomizes the encryption of the message, and sends it to the prover. The prover then tries to decrypt it, commits to its result, and at this point in time, the verifier does not learn anything about the prover. And in order to avoid selective failures attack, the verifier has to send the coins output by the coin tossing protocol. With this information, the prover can recompute the whole protocol above, and then if everything went well, he decommits, but thereby revealing the answer to the challenge. And if the two messages match, then we can be sure that the prover had enough rights to access the policy. Okay. So we actually implemented this. We have a C++ prototype implementation, and we use the predicate encryption of Okamoto and Takashima from Cannes 2011. And so you must know that there is a generic transformation from inner product to Boolean formulas of constant depth. And so the main parameter of our analysis is going to be the size of the array. Unfortunately, the depth of the formula the length of the array grows exponentially with the depth of the formulas, and this is why we have only constant depth. It would be amazing, of course, if you could push this result, but I think that would require a major breakthrough in crypto, as since these two notion of functional credential and predicate encryption, they're very entangled. And of course, if you have better ideas, I'm really happy to hear them. Anyway, so let's believe that the vector n is a good measurement for the moment. Of course, commitment is done in the random oracle model, so we use just a hash function for the sake of efficiency, and so those are essentially for free. So you can see that for a vector length of around 1,000, the running time of the prover and verifier are still in the realm of feasibility, so it means seconds. So which is that's something. It's not ideal, but at least it's a feasibility result. And interestingly enough, if we apply our functional credential scheme to oblivious RAM, then we eliminate the need for some expensive zero knowledge, which were from the original scheme. And if you compare the running time of the two authentication mechanisms in terms of number of clients, there is at least one order of magnitude of improvement in that. So that's the main take-off message of the table. And so we didn't go any further 10 clients because that's as far as the original paper goes, but we expect that the gap will increase together with the number of clients. So it seems like our solution here scales significantly better than that. Okay, so with that, I would like to conclude and thank you for your attention, and I'm happy to take questions.
Questions for Giulio?
Thanks for your talk. So a little clarification on sort of the threat model. So you say that the verifier that has been delegated the policy should not be able to learn much about this policy, right? But it seems to me that if this verifier is colluding with some possible users that have been given a credential, it can actually figure out relatively quickly what that policy is. Is that correct? Or
so what you're saying is that given a certain set of keys, you can just test your thing against that. Yeah, but yes, that you can always do, and we can't prevent that because that's part of the functionality of the scheme. But the idea is that you should not learn anything beyond that. And again, a scenario where this is useful could be when the policy is not like a Boolean policy, but it's a more complicated one. So, for example, oblivious RAM.
More questions?
In your definition of anonymity, do you consider unlinkability between two sessions from the same user?
Say again. Sorry.
So, in your definition of anonymity, if the same user has two different sessions, can those be linked, or that's not covered?
Oh, yeah. So we just gave it a unified name, but so if you go in the paper, the definition is model giving Oracle access. So you can query this object as many times as you want, and you should still, even if you query it many times, which means two sessions, you should still not be able to figure out who is who.
More questions? I have one. So these times here are in milliseconds, so that's nice and fast. But your previous slide had like 15 to 20 seconds.
Yeah. So
what's the difference between these?
Here the vector length is 10.
It's very
It's very short. If you see they are consistent.
1,000.
Yeah. So again, we didn't push it far because the original paper just considered up to 10 clients, so we couldn't compare with it. But you can see it as roughly 1 client per n. So it's still again in the realm of feasibility for let's say 1,000 clients.
Great. Any last questions? All right. Let's thank the speaker.